Hey students, let me try another video solution. This one, getting more into the practical side. So I hope you guys are liking this because you're life science people, and I wouldn't surprise me at all if a number of you ended up, being eye doctors and being a optometrists. And so maybe you'll be looking back on this someday, going, I remember those calculations. Definitely would be doing a lot of these if you, were in your optometrist school or whatever it's called. I don't think it's called med school, but your optometrist training school. And so here is, this description here. And since 22 and 23 go together, I thought I'd make, first 22 and then 23, because the first part is with contact lenses and the other one is with glasses. And so this illustrates kind of the different thought process you go through. And any of you who go to the eye doctor will know that, when you ask for your prescription and they measure your prescription, there's a different technique for contact versus glasses. And it's needed and kind of a pain. He's like, oh, look, you just examined my eyes. Why can't I have a prescription for, glasses and one for my contacts here? But there's some just other things they need to look at also. So anyways, but let's dive into this one here. Let's start with 22. Here, we have a teacher and sees that a child's contact lenses, okay, so keep that in mind because contact lenses fit right up against the eye. Prescription is 0.75 diopters. Okay. What is the child's near point? Well, let me start with the fact that the prescription is a positive number. That means the child is farsighted. Had it been negative, they would have been nearsighted. And so farsighted, of course, as the name implies, means they can see things far, but as things get closer, there is some point that they can't see clearly anymore. And that's called the near point. And so this really is saying, okay, with the child's natural but flawed eye, they have a near point. And so as long as they're looking at things at that near point or further out, they're fine. The problem is if things are getting closer than that. And in this case, well, we're asked to find what that near point really is, but that's the thinking behind these contact lenses. The idea behind the contact lens is to say, all right, we want to then make things that are actually closer than their near point appear to be further out and at their near point or further. Okay? So let me start with the standard equation. 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And maybe the first thing to do is to say 1 over the focal length is referred to as the power of the lens, measured in diopters. And, well, and diopters are inverse meters. And so this is 0.750 diopters, which I'm going to write as meters to the -1 power. In fact, maybe I'll just write it as 0.751 over meter. And I guess we could just take the reciprocal and then find out what the focal length is of these contact lenses. In fact, maybe I will, but I don't think it's really needed because, well, you can see the math here then just has 1 over the object distance plus 1 over the image distance is equal to the power of the lens. But as a curiosity, 0.75, which I guess is 3/4 inverted, must be 1.33333333. So 1.33333, and notice it's a plus. And so again, this is the focal length. And again, notice this focal length is a positive, meaning it's a converging lens. or a convex lens. And sure enough, well, I shouldn't say more about that. But what I should do then is to say, all right, here's the thinking behind the optometrist is that, okay, the lens and corrective lens we're giving the child is a 0.75. Okay. And we give them this strength because when they are looking at something close, we want it to make it have that thing close but appear then further away so that their natural eye can see it. So in other words, if we kind of set up a distance of, okay, what do we think is a good natural distance? And by default, we often use the number of 25 as the near point. And so you might want to go back to the lecture or back to the textbook. You'll hear them talk about, okay, somebody who, has, I'll just even say decent eyesight, not good eyesight, but just decent eyesight, can see things up to about 25 centimeters. They start to get blurry after that. But the truth is, when you're young, you could see things a lot closer than 25 centimeters. Again, depending on your eyes, and everybody's got different quality of eyes that seem to vary quite a bit. But for the most part, I would say young people can see things closer than 25. But the standard we like to talk about is 25. So really, here's what I'm saying in this problem. I'm saying here is take an object for this child that as close as they really need. You never want to build something so powerful that they can see it when it's a millimeter away. It just doesn't make any sense. But to make their eyes function closer to a regular eye, someone who doesn't need glasses, we're going to say, let's take something that is 25 centimeters away. And then with a certain type of lens, either positive or negative, and a certain power, we will make it appear at their natural viewing closest point, their near point. So in other words, this is going to become the near point. So that's the logic behind that. And that is important to understand because otherwise it just seems like I'm just, okay, how am I going to get a near point from image distance? And the other thing is, where does this 25 come from? And I suppose for that matter, power function to focal length. So I'm just really using this one equation, but I need to interpret as what we mean in practicality. So I get the 1 over f from the power. I get the object distance by saying, look, I want to give this individual enough lens and the right kind of lens, because they're, it's a positive lens. They're farsighted, and take something that's close. And then this is going to move it out to some distance, which is their near point. And then their eyes can naturally see it. And so if I do a little bit of work here, you can kind of see from the math, if I go 1 over image distance, this would be 0.750 minus 1 over 0.25. Maybe I'll save myself a little calculator work. That is, of course, a 4. So grabbing my calculator, I'll have 0.75, and I will subtract a 4. Oh, it's my bad. I'm not quite done. I was like, hey, that doesn't seem quite right. But that is not the image distance. I got one more step to do. I need to take the reciprocal of that. Okay. And I get, I like that number, a negative. And it's about 0.308 meters. I guess if I wanted to do centimeters, I could change it to 30.8 centimeters. I'll leave the negative in there, but hopefully that's kind of obvious. Maybe we should talk about this. But the point is, this would be their near point. It wouldn't surprise me, as I said on the other ones, if the next step, the author says near point, and they drop the negative and say it's 30.8. Because what it would mean is something like this. If this is the person's face, what does a face look like? I'll give myself a little space down here. So here's maybe a nose, some lips, chin. But their eyes are right here. Terrible picture. And the contact lenses, which is real important, especially as we go to the next problem, 23. The contact lenses are right on the surface of the eye. And so the light's coming in, and we're talking about holding an object 25 centimeters away. And with this power of a lens, we want it to be, and notice the negative distance. So for a lens, the negative is where the light doesn't go. So for a lens, the light goes through. So positive image distances would be on this side of the lens where the light goes through. So our negative means it's going to make it look like it's over here somewhere. And for those of you who've, can remember when you got your first pair of glasses, if you've got them at all, you guys are young, so you may not have it, but I didn't start wearing glasses until about age 20. And, I just remember being in college classroom and things just kept getting blurrier and blurrier, and finally realized I need glasses. When I went to the eye doctor and got my first pair, I had something like this, although I was nearsighted, not farsighted, but just things looked really weird. They just were not at the right distances. The doctor even said, be careful now going, particularly downstairs, because you could fall. Things aren't going to look right to you, so hold the hand railing. And I didn't think much of it until I left the office, and it was on the second story, and I went down the stairs, and I was like, okay, I need help getting down these stairs. And it took about a day, but eventually my eyes got used to it. And now I don't even think much about it when I put on my glasses. Things that, are really 25 centimeters away seem that way to me, even though my glasses are doing something else. Although in my case, I'm nearsighted, so they make everything look closer. But it was just kind of weird. I'll never forget it. That it just fit this description that I had learned in school. That is like, wait, you mean you're going to take something and make it look further away? Won't that, I could see how that fits my natural eyes now, but things are going to just seem inappropriate distances. And yes, I can focus on them now, but they're at the wrong distance. And I thought that would bother me. And it did, but my brain got used to it right away. And so I was like, wow, that's a trip. So anyways, I share that story. Maybe it'll be helpful to somebody someday. But anyways, there's the near point. Hopefully that helps. Take care.